Alright, so good morning everyone. Today we're going to start the chapter 5. Okay, so chapter 5 works energy and power. There are three different subtopics in this chapter. So we're going to look at them one by one. So let's begin with breakdown.
Money management.
Okay. So work, energy and power. This is quite a large topic. So there are three subtopics in this chapter. First works. Let's start with 5.1. So a work is defined as a scalar product. Now you have a new term, scalar product. If you remember what have we learned in chapter 1, then you should know how it looks like. So it is a scalar product between force and displacement. So force we have F, displacement is S. And now question tells you have a scalar or a dot product. Okay, so scalar product, W is then equals to F dot S. Okay, this dot it doesn't represent a multiply. Okay, so it represents a dot product. Okay, the things that you learn in the SEM 1. So if you recall what have we learned in the SEM 1, when you have a dot product, okay, you're going to change it into cos theta. That's why F dot S at the same time is equals to Fs cos theta. All right. So this dot, remember, it doesn't mean that it's a multiplication. All right. It is another type of product, which is known as scalar product. So when it comes to a scalar product, now the name called scalar product, it means that the result is a scalar quantity. So work done is a scalar quantity. It is not a vector quantity. All right. So W equals to F dot S, and it is equals to Fs cos theta. And what does it mean by this theta? Now, this cos theta is very important because you need to know what is the angles between F and S. All right, what is the angles between force and displacement? So these angles, it represents angle between force and displacement. So you have to see. Now, if your force is going to the right-hand side, and object is going to the, okay, let's say now you have an object. So you pull it, and then it is moving to the right-hand side. Now, in this case, both of them, they are heading towards same direction. So angles between them, okay, theta between them is 0 degree. Now, sometimes when you pull object to the right-hand side, object will experience frictional force at the same time. Okay, so work done, you can have two types of work done. One, okay, first work done is the total work done acting on the object. The second work done is by the force component. So you can calculate one by one for each of them. Okay, so first one is the total work done. And then the second one is by component. Okay, by component. So by component, you see, if you have 5 forces, then you have to calculate for all 5 of them. You have to repeat 5 different times. If you're looking at total work done, then you can use net force. Okay, you can use net force to calculate total work done. Now let's go back to this diagram. If you have a diagram like this, then what is the angles between frictional force and the displacement? Now displacement is going to the left. It's going to the right, sorry. Frictional force is going to the left. Therefore, angle between frictional force and displacement is actually 180 degree. It is very important to write it down as 180 but not 0. Why? Because cos 0 degree give you 1. Okay, and then cos 180 degree, it gives you negative 1. So negative 1 will cause the calculations becomes a negative work done. Now, what does it mean by negative work done? It means energy loss. So it is very important to know the angle between force component. And of course, when it comes to this diagram, you can actually have a 90 degree. Okay, so let's say now this is your force, your normal force N, and then this is the weight, W. So angle for normal force and weight is actually equals to 90 degree, where cos 90 degree then give you 0. So it means actually there's no work done along a vertical component if your object is moving to the right-hand side. Okay, so no work done along the normal force, no work is being done along the weight. Okay, which makes sense because now my object is moving along horizontal components but not vertical component. Therefore, no work is done along vertical component. right? So if an object is moving along vertical components, then yes, there's work done along vertical component, but no work done along horizontal components. So it depends on the angle, all right? So angle is very important. Make sure you know how to determine the angle between force and also displacement. So like I told you just now, because this is a scalar quantity, scalar product, so it is a scalar quantity. So SI unit for works is a kgm square as -2, or the special SI unit is known as joule, right? So work done, now this is what I told you. So work done on an object is 0 if angle is 90 degree, okay? Or F is equal to 0 or S equals to 0, means object is not moving. So if object is not moving, of course there's no work done, okay? And then if object has a net force equals to 0, have a force equals to 0, then there's no work done as well, right? So theta is equals to 90 degree. Okay, now sign for work done. This is what I told you just now. Okay, it is important to consider the sign conventions in your calculation, because it tells you whether the work is done on the system or the work is done by the system. So work done is positive if the work is done on the system. Now, what does it mean by work is done on the system? So let's say if you have an object, okay, and then you push it. So if you are the one that pushing the object, then we call it work done on the system, because the work is being done by you, right? The work done is being done by external force. Now, what work done by the system? So what does it mean by work done by the system? For example, the frictional force, okay? So the object is doing the works because it wants to move, okay? It's doing the works to overcome frictional force because it wanted to move. So that is the work done by the system. So in that case, we have a negative value, all right? So work done is positive if work is done on the system. So you remember the keywords. Sometimes question will tell you work is done on the system or energy is transferred to the system. Then you yourself have to know the works given is positive. If the questions mentions work is done by the system or it is transferred out from the system, then you yourself have to know that the value given is a negative value if you are not given the angle. All right, so if you're not given the angles, then you have to look for the keywords, see whether the work is done on the system or it is done by the system. It is transferred into the system or it is transferred out from the system. So these are the keywords that we use to distinguish whether the works given is positive or negative. So again, in this chapter, we have another graph, which is known as a graph of force against displacement. So in this case, okay, the diagram already tells you work done is equal to the area under the graph. Okay, so basically you just rewrite it here. So work done is equals to area under Fs graph. So up until this subtopic, how many graphs do we have right now? So let us do a quick recall. Chapter 2, we have S against T graph, where its gradient, okay, represents velocity. Area, now area has no meanings, but when you have a V against T graph, gradient give you acceleration, and then area, it gives you distance. Okay, give you distance. And now when you have an AT graph, actually the area give you velocity, but it has no, the meaning, it's not very meaningful value, all right? It's not a very meaningful value. And then in the previous chapter, we have a FT, which is an impulse. Impulse, then you have a what? You have an area equals to J. And then in this chapter, we have Fs graph. So Fs graph, it gives us area equals to work done. So basically, these are the types of the graph that we have seen so far. Okay, we have 5 different graphs where it's a gradient and area has a different meanings. So make sure you memorize all of them, because in exam, all these item, it won't be given. Okay, all these graph, the definitions of the graph, what can you find from the graph, what can be found in the graph, then all this won't be given in the exam. You yourself have to memorize it. Okay, next we have energy. So just now we've seen what is a work done. So work done, we have two different types of work done. One is a total work done. Total work done can be calculated by using net force. And then we have work done by each component. Okay, so work done by each component, you calculate one by one. And then from there, you can actually determine the total work done as well. Okay, you can actually determine the total work done as well. So for example, you have an object. So a force, F, external force, and then frictional force, and then a normal force, and then a weight. And that object is moving to the left. So you calculate work done for each of them. Okay, so let's say you calculate work done for external force, work done for frictional force, work done for normal force, work done for gravitational force. So total work done can also be calculated by adding them up. Okay, so when you add them up, they become W total. So W total, you have two different methods to calculate it, either by using net force or either by using the work done from each component. Okay, work done by each component, then you add them up, then it is also equals to total work done. So or W total is also equals to F net dot S. Okay, so you look for the net force. So previously we use a force by component. If you want to calculate total work done, then you use net force. So how to calculate net force? You have learned it in chapter 4. So this chapter, you need a bit of information, a bit of knowledge from chapter 4. Okay, next subtopic. So this is a next major subtopic in chapter 5, where we have energy and also conservations of energy. So state the principle of conservations of energy. Again, you have the terms conserve. So the words conserve, conservation, it tells you what? It tells you before and after they have same value. All right. So again, when it comes to the conservations, you need to conduct the assumptions, the experiment in an isolated system. So isolated system, again, what does it mean? It means it is not being affected by any external factor. All right, it is not being affected by any external factor. It means that you carry out this experiment in an ideal situation. So no air resistance, nothing. Okay, the condition is perfect. So in an isolated system, the total energy is constant. All right, so total energy is constant. So why is it constant? Because total initial is equals to a total final. All right, total initial is equals to the total final. So therefore, it is always constant because the value is not changing. So summation E is constant if total F is equals to 0, or we can say summation E initial equals to summations E final. So this one, students always have a misconception. Why? Because, for example, now when you drop an object, okay, when you drop an object, it doesn't matter where is the object. It could be at here, it could be at here, or it could be at the ground, okay, the moment it reaches the ground. So at this 5 position, all the energy, they are all constant, not just referring to the initial and the final position. So students always have a misconceptions when it comes to these equations, okay, because you look at these equations, it says initial and final. So students always thought that this is initial position, this is final position. In fact, it is wrong. It depends on where are you looking at, which object you're looking at. If you want to determine the value at this positions 1 and also this positions 2, then we take position 1 as initial, position 2 at final. Okay, it doesn't mean that object is only at its final position when it reaches the ground. It could be at any position. Okay, it is up to you to choose where is the initial, where is the final. You can also take position 2 as initial, positions okay, this is 3, this is 4. Okay, you can also take position 2 as an initial position and then position 3 as a final position. It is totally up to you. Okay, but when the object is in an isolated system, energy is always conserved. Means that energy at every single position, the total energy, they are always the same. All right, so don't always assume initial is positions 1, final is position 4. That is wrong. It is up to you to choose where is the initial, where is the final position. All right, so initial and final, don't get the wrong idea. Make sure you know the meanings of initial and final. You are the one that decide. Okay, you are the one that decide. So mechanical energy is a sum of kinetic energy. Now, when it comes to mechanical energy, in your syllabus, it refers to kinetic, and also potential energy. Okay, these two energy, they are the main focus in this chapter. So we are going to focus on kinetic and potential energy first. So mechanical energy is the sum of kinetic and potential energy in an object that is used to do works. So kinetic energy of a body is due to motion. So if question asks you what is the difference between potential energy and kinetic energy, the main difference is this one. Kinetic energy is caused by motion. Gravitational potential energy is caused by position. Elastic potential energy is caused by stretching or compressing. Okay, the situations, the conditions. Either you stretch it or you compress it. So this is the differences between these three types of energy. All right, so potential energy, we have two different potential energy. One is the gravitational potential energy and another one is elastic potential energy. So every types of energy, it has its own keywords that we use to identify it, we use to differentiate it. So make sure you know the key terms, because it was one of the past year exam, past year question, that it asks the students to state what is the two differences between kinetic energy and gravitational potential energy. The first difference is a motion and position. One is caused by the motion, one is because of its position. Now, what is the second difference? This is a very tricky part. Okay, the things that students couldn't think of, even though it is very simple, very easy. Okay, even I myself don't believe that is an answer. So the second difference is the equations. They consider it as one of the difference. So 2 marks is given. Okay, if you state first the difference, the kinetic energy is due to the motion and potential energy is due to the position. And then second mark is given if you state the equation for each of them, where K is equals to 1 over 2 mv squared, and then gravitational potential energy is UG equals to mgh. Okay, UG equals to mgh. So these are the two differences between K and UG. So in exam, you cannot straight away just write down kinetic energy is due to motion, potential energy is not due to motion. In that case, you won't be given any marks. Right? Kamu tak boleh sebut satu disebabkan motion, satu bukan disebabkan motion. That is not differences. Alright, what you have to say, one is caused by motion, another one is caused by position. You need to mention both of them in order to get 1 marks when the question asks for differences between two items, two objects. Alright, so that is how you answer exam question. So if question asks you what is the differences between the gravitational potential energy and elastic potential energy, then you need to state clearly. Gravitational potential energy is caused by position. Elastic potential energy is caused by stretching or compressing. The second difference that you can state is gravitational potential energy equation is UG equals to mgh, whereas the equation for potential energy, now potential energy, you have a US. Okay, now this S, we use subscript S because it often happens in a spring. Okay, or a storing force, restoring force. So it is equals to 1 over 2 kx squared, or at the same time, it can be written as 1 over 2 fsx. Okay, so F is the restoring force. Now, what does it mean by restoring force? It is the force that tries to bring the object back to its initial condition, its initial position. So for example, now you have a spring. Okay, you pull the spring. You are the one that stretch the spring. So this is a wall, for example. Now you stretch it by an external force. So the force that you exerted is the stretching force. Okay, you cause it, you pull it. And at the same time, if you pull a spring, you will feel that it seems that it always wants to go back to its original position. That is because there's an internal force, which known as restoring force, stored in the spring. Okay, that tries to bring the spring back to its initial condition. So you exert external force on the spring, and spring itself, okay, tries to brings it back to its original condition, original shape. So the restoring force is being stored in the object, and it is caused by the elastic potential energy. Okay, it is because of the energy stored inside the spring itself that tries to bring the object back to its initial position. So don't get confused between the restoring force and also external force. All right, restoring force always opposite to the external force. For example, now if you compress a spring, okay, if you compress a spring, so this is a spring, so what happens now? You compress it, okay, you push it. So this is a spring, but now you're pushing it, okay, you're pushing the spring. So this is the external force. So when you push a spring, what is going to happen? This spring will try to push you back, will try to go back to its initial shape, okay, by pushing the external force. All right, so this restoring force is always in the opposite direction because it tries to overcome the external force. It tries to go back to its original shape. So restoring force always opposite to external force. So elastic potential energy now is can be calculated by U equals to 1 over 2 kx squared. So k is a spring constant. Okay, that's why in elastic potential energy, I use a subscript S here because usually it can be found in a spring. All right, usually we use it for a spring. And then equals to 1 over 2 Fs x. So Fs is a restoring force. So x is either extensions or compression. Extension, positive x, compression, negative x. So you can have a negative value here, right? But the negative, when it comes to calculations, usually we don't look at it much in elastic potential energy. Okay, we seldom look at it. Okay, now let's look at this one. Okay, now you throw an object. So, yeah, the diagram is too large. Okay. Okay, never mind. So now you throw an object. Okay, so object, when you throw it, at this position, before object leave your hand, this object is having just a potential energy. This potential energy, it exists because of what? Because of the height. Okay, because of the height of the object. So this potential energy, initially, because it's not moving, because you're holding it, so initially, summations E is just equals to U. Okay, potential energy. When you drop the object, okay, it is somewhere in between the highest point and the ground. Then at this position, we say summation E is equals to K plus U. It has both kinetic energy and also potential energy. And the moment it reaches the ground, and at this position, we know that H is equals to 0. Therefore, what do we have? We have summation E just equals to K. Okay, just equals to K, kinetic energy. So even though at this 3 position, total E, summations E is equals to difference variable, the formula is different, but then the total value, okay, let me label it, summations E1, summations E2, summations E3. So U at positions 1, K at positions 2, U at positions 2, K at positions 3. Now, even though these 3 position, they have different formula, but because we assume this experiment is being conducted in an isolated system, we ignore air resistance. Therefore, we say summations E is equals to a constant value. Okay, so we say summation C is equals to a constant value in which it carries a meaning. Summations E at positions 1 is equals to summations E at positions 2. It is equals to summations E at position 3. Okay, at positions 3. So if you expand this equation, it's actually U1 equals to U2 plus K2 equals to K3, right? Equals to K3. So you just think of it like this. Now let's say you have this one, okay, tube. Okay, kamu ada 2 tube. Tak cantik. Wait, let me redraw it. So now you have a 2 tube, 2 test tube. So initially, you have only the water in this tube. All right, so water in this tube, let's call it U. Okay, this tube is U, this tube is K. So what happens when you drops the object? So when you drops the object, you're actually pouring the water, transferring the water from one tube to the other tube. All right, so let's see. Now this is a tube. I redraw it here. So tube U, tube K. So initially this one is full with a liquid, okay, full of water. This one is empty because you start from the first position. What happens at the second positions? Now, let's say this is a midpoint. So when it is located at midpoint, what happens is now you pour the water from tube U to tube K. Okay, so now this one becomes half and this one also have half. But the total volume is still the same. Therefore, we say total E is still equals to total E1. All right, summation E2 is still equal to summation E1 because the volume of the waters, they are still constant. They are still the same. And then when it reaches the final position, what happened is now you pour all of the water from tube U into tube K. Okay, so now tube K is full, full of water, but tube U has becomes empty. All right, so the moment you drop the object, actually you are starting to pouring the water from tube U to tube K. So every position, the volume is changing, but then the total volume is still the same. That is the concept of conservation of energy, right?
Oh.
Yes. Any questions?
Faham.
Huh? All right. If no, then let us continue. So next one, if you look at the diagrams on the right-hand side, so just now is about the potential energy and kinetic energy. So the one on the right-hand side is a potential energy because now you have a spring. So for unstretched spring, if you look at the diagram, unstretched spring total potential energy is equal to 0. Means that the object is now at its initial position, at its original position. And the reason why it is equal to 0, because your x is equal to 0. All right, your x is equal to 0 at its initial position, at its original position, before you stretch it or before you compress it. Right, before you compress, before you stretch, it is equals to 0. And then Hooke's law. Okay, now Hooke's law states that the restoring force of a spring is directly proportional to the amounts of stretch and compression. Okay, if the limit of proportionality is not exceed. So you need to know the equation for Hooke's law as well. So Fs equals to negative Kx. So Fs is always opposite to the x, okay, opposite to the stretching, the stretch or the compression. Okay, why? Because like I told you just now, if you have a spring and you pull the spring, okay, you pull the spring. So this is a spring before you pull it, before you compress it. So initial, okay, original length is here. So original length, we are going to take it as x equals to 0. All right. So when you stretch the string, this stretching is known as x, okay, and this x is a positive value, okay, this x is a positive value. So F external, okay, F external. So when you stretch the spring, the displacement increase in a positive direction. This is positive x. But when you stretch the spring, what I told you just now, restoring force is always opposed to the external force. Why? Because restoring force is the force that tries to bring the spring back to its original state, original condition. So Fs is in the opposite direction. That's why when it comes to this proportionality equation, it tells you Fs is always negative to x. Okay, it's directly proportional to negative x because it is always opposite to the directions of x. All right, it is always opposite. So here it mentioned Fs is always opposite to x. So if you compress the spring, okay, now if you compress the spring, so what happened is, okay, so this is still our x equals to 0. X equals to 0. So the amounts that you compress it, this one we call negative x. Okay, negative x. But now the restoring force is the force that's trying to push the spring back to its original position. Therefore we have Fs going to the right hand side, which is a positive force. Okay, so positive force. So displacement is going to the left, and then force is going to the right. So they are always opposite direction. It doesn't matter whether you compress it or you stretch it. Okay, you stretch means that this spring, the displacement is going towards positive direction. You compress it means that it's going towards negative direction. Okay, so they are always opposite to each other. That is the reasons why Fs is directly proportional to negative x. Negative sign is very important. It tells you it is always opposite. All right, it is always opposite. So let's see next. So for a spring constant, we can find US by Fx graph. So now you have one more graph, which is a F against X graph. Okay, F against displacement graph. So the gradients of the graph, it represents the coefficients of a spring. Okay, why? Because you have F equals to negative Kx. So the gradients of the graph, it represents the coefficients, the K. Okay, and then the work done is the area under the Fx graph. So by just looking at this graph itself, you can get two pieces of information. Area under the graph represents work done, and then the gradients of the graph represent spring constant. So basically just now based on the equation, we were talking about Fs, right? So now you just replace S, the displacement symbol, from S into X, into X, okay? X, we use it for spring. So basically it still refers to the same graph, okay? Same Fs graph. So sama saja Fs dengan Fx, just that they uses different symbol. All right, they uses different symbol. So which means by just looking at this graph, Fs graph, what is the information that you can get? You can get work done, okay, work or energy, US, and then you can get K, spring constant. So two pieces of information can be obtained from the graph. All right, so we are done with energy. Next, we're going to look at conservations. So conservations of mechanical energy. Now, when we talk about conservations of energy, we don't say kinetic energy is conserved. We don't say potential energy is conserved. Okay, the things that is conserved is the mechanical energy. So total K, or we say E equals to U plus K equals to a constant value. Okay, so that is the meanings of conservations of energy. So from here, we can then expand a lot of difference in equations. Okay, we can get a different equation. So for instance, the equations that we often use is a summations E initial equals to summations E final. And then initial, because you are looking at U and K at the same times, therefore initial U, okay, plus initial K equals to final U plus final K, sorry. Okay, final K. So E equals to U plus K equals to a constant value. At the same time, it can be written as this one. Summations E initial equals to summations E final, or U initial plus K initial equals to U final plus K final. Now, this equation is a must in your exam because you will be given 1 mark by just writing down this equation. All right, 1 mark is given for just this equation, K1, because it means you understand the concept. It means you know that the energy must be conserved. Okay, the mechanical energy must be conserved. So in the image on the left-hand side, the total mechanical energy at any point. So this is what I told you just now. You don't get a misconception says that only the initial, okay, only this part and this part, they are conserved. No. Okay, it is conserved at any point, including the one at the half K and half U. Or even if you are looking at maybe here you got another position, here you got another height. Okay, all these 5 positions, the total mechanical energy, they are the same, they are constant. Okay, so E equals to K plus U, so equals to 1 over 2 mv squared plus mgh. So if a K1, U1, K2, and U2 are the kinetic energy and the potential energy at 2 different positions, so you can rewrite it in this form. So this is basically the equations that I give you just now. All right, it's coming from the equations that I give you. So you choose 2 different positions. All right, you choose two different positions. It's up to you to determine where is the initial, where is the final. As long as you know the energy, the total energy is conserved. So this statement basically it has nothing to do with diagram. Alright, ayat ini dia tak ada kaitan dengan diagram. Diagram just shows you the energy is conserved at any point. So starting from the first point, you have a full bar of potential energy, and then when it drops until half U and half K, so the bar of the blue color bars becomes half, the K increased by half. And then when it reaches the ground, K is a full bar now, full kinetic energy, but U becomes 0. So this is what I explained it to you just now. All right, so a statement on the right-hand side has nothing to do with the diagram. So the statement on the right-hand side, it tells you now, if you simply choose 2 points, okay, one as an initial and another one as final, then this is the equations that you have to apply. All right, so you choose any 2 points, as one as an initial and one as a final. Now, conservation's energy with dissipative force. Just now, we were talking about various possibility, but all of them, we assume there's no frictional force, there's no air resistance. But in reality, that is quite impossible. Okay, in reality, that's quite impossible. Why? Because object often move with energy loss. Okay, always experience energy loss because of various factors, especially kinetic energy and also resistance. All right, so in this case, in our syllabus, we're going to look at frictional force, the energy loss due to friction. That would be our main focus. So dissipative force, such as a friction, air resistance, push or pulls by a person, and etc., do not conserve mechanical energy. Okay, all these external force that caused by you or caused by a frictions, caused by a resistance, they all causes the equations becomes the mechanical energy becomes not conserved. All right, but however, with these forces are taken into account, the total energy is still conserved. But now you don't call it conservations of mechanical energy. Now it's just conservations of energy because it includes all the other dissipative force. All right. So mechanical energy is no longer conserved, but total energy is still conserved, provided you take into considerations the energy loss in the system. So energy loss can be calculated by using WF, all right, when it comes to frictional force. Sometimes questions will give you value. If you want to calculate the conservation of energy, if object experience energy loss due to air resistance, then usually the types of questions will straight away give you the values of energy loss. But most of the times, you'll be given questions that has a energy loss due to friction. Then you yourself need to calculate W first. Okay, you yourself need to calculate WF, which WF is equals to frictional force S and then cos theta. This theta is between frictional force and S. And then it will give you Fs cos 180 degree, which is then a negative value. So it is a negative value. So your object experience energy loss, okay, because WF is a negative value if you calculate it correctly by using cos 180 degree. So these equations basically is kinetic energy plus potential energy minus energy loss equals to final kinetic energy plus final potential energy. So WF is the energy loss. This energy loss is caused by friction. Okay, if the questions wants you to calculate. If it is a value that cannot be calculated, for example, air resistance, then usually straight away, questions will give you E loss equals to maybe 10 joule or 20 joule like that. Then you yourself straight away substitute into the equations by using minus 10 joule, minus 20 joule. So energy loss is a negative value. All right, energy loss is a negative value. So this is a conservation of energy with dissipative force. Just now is a conservation of mechanical energy. So make sure you know the difference between them. So next, state the work energy theorem. So now we want to link work and energy together. All right, just now we were looking at the work as W equals to F dot S, and then energy we look at them in terms of K in terms of UG, in terms of US. Now what we want to do, we want to link them together. Okay, we want to link these two things together by using work energy theorem. So work done on an object is equal to the change in object kinetic energy. So work energy theorem is actually talking about the kinetic energy. So W net, okay, the net work done, the total work done is equals to change in kinetic energy, which is then equals to K final minus K initial. Okay, K final minus K initial. So like what I told you in 5.1, if you want to calculate net work done, which is the total work done, you use F net. Okay, so W net, F net. So net force is being used to calculate net work done. So F net as cos theta is equals to 1 over 2 mv square minus 1 over 2 mu square. So initial velocity and final velocity. So according to the work energy theorem, a moving object has kinetic energy because the work was done to accelerate the object from rest to a speed v, okay, or from an initial speed to a final speed v. So work energy theorem is change in object kinetic energy. Just change in kinetic energy, yeah, not change in potential energy. If you are looking at change in potential energy, then that is not work energy theorem. Work energy theorem only tells you the relationship between W and also kinetic energy. All right. So work done by force of gravity. So gravity also do force, okay, if you drop an object. So gravitational force is a well-known force that can do positive or negative work. So the figure below helps to show how the work can be determined. So WG equals to Fs cos theta. If you look at this diagram, now you drop this object. So S is going down. Displacement is going down. If S and W, they are both heading towards same direction, then we use cos 0 degree. Okay, we use cos 0 degree. So W equals to mg, and then initial height minus final height, cos 0 degree. So you expand the equations, Wg equals to mgh minus mghr, and then W equals to u naught, u initial, minus a u final. So if you look at this equation, it tells you Wg at the same time is equals to negative del u. Okay, negative, the change in potential energy, which is also equals to negative u final minus u initial, right? So this one, okay, this one, it just shows you the relationship between work done by force of gravity and potential energy. It is not your work energy theorem. Jangan salah faham, even though it looks very similar to the previous example, to the previous work energy theorem, but this is not work energy theorem. This is simply work done by force of gravity. Okay, don't get confused. So work energy theorem, remember, it just involves kinetic energy. This one is just an additional knowledge to show you how to calculate the work done by force of gravity. So you can calculate it by using Wg equals to negative delta U, so which is equals to negative U final minus U initial. So this equation is valid for any path taken between initials and height. Okay, initial and final height. So basically, this equation is valid for any vertical displacement. Okay, there's only the difference in vertical distance need to be considered when calculating the work done by gravity. So this example is when you drop an object. Now, if you lift an object, if you take it up, okay, you lift an object. This is okay, maybe you pull it up or you throw it upwards. Okay, or let's say you throw it upwards. So now if you throw this object upwards, the S is going up, but W is going down. So in this case, our W will then be equals to Fs cos 180 degree. So that is the meanings, that is the meanings of this statement. The gravitational force is a force that can do a positive or a negative works. It depends on the direction. Okay, it depends on the directions that you throw the object. Whether you throw it upwards or you let it drops. If it throws up, then it is doing positive works because you are doing the works that is the work is being done on the object to cause it to move upwards. But if it drops an object, then this object itself is doing the works, okay, by using its own weight. So it do works by itself. So this is a very good example to show you the difference between positive and negative work done. So the diagram on the right hand side is a positive work done because you are the one that doing works. Okay, you do works on the object, therefore this object can move upwards. Okay, this object can move upwards. You do works on it. And then the diagram on the left hand side is a negative work done. Why? Because the work itself is being done by the object. Okay, how did the object do works? It do works by using its own weight. So the moment you drop it, it will go down. Why? Because the weight, the object itself is doing works. So this is the work done by the object, and then this is the work done on the object. Okay, the left hand side is by the object, the right hand side is on the object. So basically, one is more to its own nature, one is because of the external factor that causes it to move. Okay, so that is the difference between on and by. All right, so done. We are done with energy. Now let's look at power. Okay, let's look at power. So power is defined as the rate at which work is done. So you are looking at how fast work is being done on an object. So the average power is equals to the work done divided by times. So P average can be written as delta W over delta T. Okay, delta W over delta T. So this is average power. So average, you have an initial, you have a final position. And then you have instantaneous power again. So you have the term instantaneous, which happened at just one position. So instantaneous power, okay, is equals to dW over dt because it happens at an infinitely small times, okay, small period of time. So P instantaneous equals to dW over dt. When you expand this equation, it is equals to d over dt. Now W equals to F dot S. That is based on the definition. So therefore, we sub it into the equation. So P instantaneous, you differentiate F dot S. So rearrange the equations. P instantaneous equals to F dot ds over dt. Now this ds over dt, according to the definitions of velocity, instantaneous velocity, v is equals to ds over dt. Therefore, P instantaneous can be written as Fv as well. Okay, Fv as well. But don't forget about the dot. Okay, dot tak hilang lagi. Dot masih ada. So yes, this is a dot. Okay, the dot is a bit small. So dot is still here. Okay, dot is still here. The dot is still here. So P is equals to F dot V. Therefore, the equations can be written as Fv. Now, because you have a dot product, you have a scalar product here. It is equals to Fv cos theta. Okay, Fv cos theta. So that is how you differentiate the equations. Okay, that is how you use the equations. So from instantaneous, okay, you derive it. You differentiate work done until you obtain P instantaneous equals to F dot V. So you have two equations, but you need to know which one for which situations. The first one is for average power, and the second one is for instantaneous power. So instantaneous power, again, it refers to the power happens at just one position, just one point, all right? So since work done in a process involves the transformations of energy from one type to another, power can also be written as P average equals to delta E over T. Okay, delta E over delta T. So it's defined at the rate at which energy is being transformed. So usually this delta E, we just look at the one of the mechanical energy, either delta K or delta U over T, right? So this one you will have a better idea when you go through the exercise in your tutorial class. All right. Power is also a scalar quantity because it involves a scalar product, as you can see here. P equals to F dot V. So obviously it is a scalar product. So therefore it is a scalar quantity. So SI unit for power, okay, first one is a joule per second, or it is watt, okay, or is watt. And of course it can be written in a base SI unit as well. Okay, you yourself try to derive it. Kamu sendiri derive base unit untuk power. So this is a special SI unit, joule per second, another special SI unit, which is a watt. So two special SI unit can be used for power. So for practical purpose, a larger unit is often used, which is known as horsepower. 1 horsepower is equals to 746 watt. Okay, so 1 HP is equals to 746 watt. So this one, we seldom see it in our syllabus. Okay, kita jarang nampak ini dalam syllabus kita. You will see horsepower very often in the university books. Alright, you'll see horsepower very often in university book, but not in a matriculation syllabus. So if it come out in the exam, I think the value should be given because because it's seldom. We seldom see it in our books, and it is not part of our syllabus. So this is just extra knowledge for you. Right. So that marks the end of this chapter 5. So we have seen what is work done. We have seen how to calculate work done, and then we have seen what is energy, how many types of energy do we have, what is the conservation of mechanical energy, what is the conservation of energy with dissipative force, and then we have seen the work energy theorem, which is the relationship between W and delta K, and we also learned what is the work done by gravitational force. So from work done by gravitational force, we try to identify the work done on the system and also the work done by the system just now. And then the last one, we have the power. So power, basically, there's nothing much to learn. Okay, all you have to know is just to know the equation. Which equation is for average power? So equations, P equals to delta W over delta T is for average power. And then equations, delta E over delta T is for average power. And another equation, P equals to F dot V is for instantaneous power. And then at last, it tells you, okay, another unit that we often see in a university in our real life is horsepower. For example, your aircon, 1 HP, 2 HP, actually is referring to the horsepower. Okay, so 1 HP is equals to 746 watt. So I think that's all for today. Any questions that you would like to ask? Any questions? Masih hidup ke atau sudah pengsan?
Hidup.
Oh, masih hidup belum pengsan. So in the lecture, this is what we are going to do. I introduce the theory to you. I explain the theory to use. I give you the equations. And then how to use it, you're going to use it in a tutorial. So if no questions, I think that's all for today. You may leave the class now.
Thank you, madam.
Thank you, madam.
Thank you.
Thank you, madam.
Thank you, madam.
Thank you,
Thank you, madam.
Thank you, madam.
Thank you, madam.
Yeah.
Thank you, madam.
Thank you, madam.